Hello. Thanks to everyone watching for allowing me to speak with you. I'm Frank Santaguida, Vice President of Exploration for First Cobalt Corporation. My talk is about challenges and opportunities of establishing a cobalt supply chain here in the US and in Canada. This presentation may contain forward-looking statements. The talk is not necessarily meant to promote First Cobalt, but is our perspective on this important issue. Cobalt is deemed a critical mineral in the US and in Canada. Critical minerals are conventionally defined by their use in power and energy generation, as well as the risks of their availability within the global supply chain. Considering these factors, cobalt ranks highly along with the rare earth element metals. This talk will highlight why cobalt ranks so highly and what is being done to address this criticality, specifically the supply risks here in North America. Let's first take a look at the history of cobalt and the demand trend over time. Cobalt has been in use for hundreds of years, first within pigments and dyes, then its widespread use in steel and metal alloys. Development of new mines worldwide and improvements to mineral processing made cobalt readily available in the 20th century. The use of cobalt and lithium-ion metal batteries developed in the last 20 years has created an increasing spike in the demand trend to where we are today, which I would call the battery era for cobalt. Cobalt use in the batteries that power electric vehicles are driving demands to triple beyond the current production levels. EV sales are growing in leaps and bounds. In 2020, sales in Europe surpassed China, who have long adopted driving electric cars and buses over combustion engines in a move to reduce their city smog issues. The uptake of EVs worldwide will sustain the growing demand for cobalt for many years to come. So let's start with a look at the supply chain to first see where cobalt comes from. Cobalt is rarely in a mineral form where it is the only metal. Cobalt is typically a byproduct metal within nickel and copper ores, and this is naturally inevitable due to its chemical affinities of cobalt, nickel, and copper. Almost all nickel mines contain some cobalt, found all around the world. Cobalt is present in some copper deposits, specifically those within the Democratic Republic of Congo and Zambia in southern Africa. It's estimated that 60% of global cobalt resources reside in these deposits. Many of the mines in the DRC are Chinese-owned. As a consequence, the supply flow of cobalt moves to Asia, specifically to China, where most cobalt refineries are in operation. The small amount of cobalt produced in Canadian nickel mines is all shipped abroad to mostly Europe, as well as small amounts to Asia. All of the cobalt that's processed in Europe are mainly processed for use in steels and alloys, and very little of the cobalt for sulfate production that's used in battery manufacture. In China, the Chinese refineries produce over 80% of all cobalt sulfate for battery production. Therefore, the US is 100% reliant on imports of cobalt for use in battery manufacture. This is creating a vulnerability. Compounding this economic issue is the cobalt conundrum, that the world seeks to move to greener energy sources, but it in part comes from countries with poor worker safety standards and poor government practices, and sometimes outright corruption. We'll remain in this state for several years unless changes are made. The so-called cobalt conundrum associated with the supply problem is being closely watched by the battery manufacturers and EV companies. Lower cobalt content to batteries are being trialed. Currently, the 622 battery is used in EVs with 2 cobalt ions for every 6 nickel and 2 manganese being the convention. Configuration with higher nickel and manganese are the 811 batteries. But considering the predicted sales in EVs to 2026, an additional 4 times the current cobalt production is still needed, so the demand is still expected to increase. So what can be done? Let's look at the resource perspective of cobalt in the ground. A few, namely 3, individual DRC mines dominate the cobalt supply chain. The remainder are spread to Cuba, Mauritius, Pacific Islands, Morocco, Australia, Canada, and Finland. Cobalt in the DRC deposits is both high grade and high tonnage compared to others globally. The deposits occur in a relatively small region constrained by a favorable geological setting for cobalt and copper, unlike any other in the world. Ore minerals are also simple and easy to concentrate, making mining and mineral processing operations lucrative. Processing operations are large in size, collecting ore from several mines, and consequently controlled by only a few companies. In North America, cobalt production is centered on Canadian nickel operations, although prospects do exist elsewhere. Most significant of these are in Alaska, the Northwest Territories, Idaho, Montana, Missouri, and in Minnesota. The other prospects are quite small in size and may not be significant to change the demand. A major cobalt resource within the U.S. lies within a string of copper-nickel deposits along Lake Superior in Minnesota, within a geologic domain considered the Duluth Igneous Complex that stretches across to Michigan and up to Canada. These deposits are low in grade with only hints of cobalt, but are large in size. These are unmined largely due to environmental concerns. The U.S. Geological Survey has found the largest unmined cobalt resource in America lies within Idaho, where many deposits lie within a continuous metasedimentary rock belt that extends over 60 miles near the towns of Salmon and Chalice. The Blackbird mine was an active producer over 60 years, but has long since been closed. In 1954, production from Blackbird accounted for 50% of the U.S. cobalt production. Mineral exploration has now been active throughout the belt, with 2 deposits at an advanced stage for mining in the next 2 to 5 years. The belt could contribute a significant quantity of cobalt to feed battery manufacturing plants being built in the western U.S. The mineralization style in the cobalt belt is diverse. Individual deposits range in size from small, high grade, such as at Blackbird, to medium sized, lower grade, such as at Iron Creek. Further variation in ore minerals also allow for several mining and processing styles to be considered. Combined, the Idaho Cobalt Belt deposits are a globally significant resource in line with some of the DRC deposits. High grades typically equate to easier mining extraction, so are preferred targets for development compared to the large, low-grade deposits such as within the Duluth area in Minnesota. Grade is not the only consideration to mine development. The mineral host to cobalt is also a key with respect to the other metals in the cobalt ore minerals. The DRC ores don't contain toxic metals like arsenic and contain much lower contents of iron, therefore easier and cheaper to process. The Idaho ores, being higher in arsenic and iron, have been thought to be less attractive until now. Dedicated cobalt refineries are capable of processing the more complicated cobalt ores. The first to come online in North America is set to be commissioned in 2022 after completing advanced feasibility studies in 2020 showing a positive production scenario of 25,000 tons of battery-grade cobalt material. That represents 5% of the total global refined market. The facility is relatively small in size and utilizes modern processes without generating toxic emissions or liquid waste material. The plant is a great example of an end product processing operation that can be suitably developed elsewhere in North America when other domestic resources are brought into production. To address this economic barrier to developing U.S. cobalt, plus looking at other critical mineral issues, the Department of Energy created the Critical Materials Institute. In 2018 and 2019, one project by the Colorado School of Mines was completed, targeting new selective extraction methods to separate cobalt from arsenic. CMI continues to fund research and development projects, and a new call was put out in 2020 to consider improved methods of extraction of critical minerals and complicated ores. One project that has been approved will look at new alternative methods to concentrating cobalt from pyrite at the Iron Creek deposit in Idaho. Systematic testing at the Colorado School of Mines using methods that are more energy conservative or can reduce the amount of waste material will be conducted. Positive results from this project on the cobalt ores can be applied to other similar pyrite-bearing deposits elsewhere in the United States, so the work could be game-changing with regard to having a domestic source in North America. The message I'd like to leave everyone with is positive. Changes are happening to establish a domestic cobalt supply chain that will be needed to sustain the EV market. On the downside, though, we are likely over 5 years away from being significantly less dependent on cobalt imports due to barriers that impede the timelines. These barriers are not walls. Extraction methods to improve mineral processing of cobalt ores are emerging. Permitting timelines set by government are being streamlined to effectively review mining and mineral processing projects without sacrificing considerations to the environment, local communities, and wildlife. I think the largest barrier to mining and mineral processing project timelines is the public sentiment to our industry that remains mixed. We need to do a better job of promoting ourselves, showing the great advances that have been made and technologies being used. For example, the first all-electric, non-diesel underground mine has opened in Canada in this last year. Other new mines and existing operations are being redesigned for lower carbon footprints and reduced environmental impacts here in North America that all show we can deliver critical minerals such as cobalt more responsibly than many other places in the world. I'd like to thank everyone for their attention. I can take any questions now or to the email address on this slide.